All right. Hi. Evening. I'm Ross Andrews. My interests are volunteering for things and looking dumb in front of crowds. Um, and a lot of people here have asked for kind of a basic intro to just the very basics about electricity and circuit building. Um, Usually in these meetups, it's kind of a bimodal distribution of some of us, like me and Travis, are building super complex things, and other people are struggling making an LED flash. And so I'm trying to sort of bring that second group into where the rest of us are by kind of giving just a basic primer on how all this works, what it all does. This is probably going to be like, you said you just graduated with a computer engineering degree. You probably are going to know most, if not all of this already. Please correct me if I get anything wrong, since I don't have a computer engineering degree. I graduated with computer science, so as far as I know from school, the hardware is the thing that you kick when it stops working. But most of this, I actually, ordinarily in these I say that I'm entirely self-taught, because most of the time when I do a presentation, when I do a presentation, I am. But this time, actually, this stuff I did learn in high school physics class. So that's pretty much the level of what this talk is going to be. So to begin with, that is actually showing. Cool. So, and my notes aren't. Great. So everything in the universe is made up of extremely tiny subatomic particles. And each of these things has a set of properties, like spin or mass would be one, or one of them that's very important is charge. Everything has a charge, either a positive charge, a negative charge, or a neutral charge. So protons have 1 unit of positive charge, neutrons have no charge at all, and electrons have 1 unit of negative charge. Just like the mass property is the way in which that particle interacts with a gravitational field, charge is the way in which it interacts with an electrical field. So the idea is that everything with the same polarity of charge will repel each other, and everything with opposite charges will attract each other. Anything that has a charge is going to throw out an electric field, and other charged things will be affected by that in some way. By the way, I want to thank Aspen for the slides, because I sent her the notes that I had made for the talk, and she made a slide deck. So, because these things are attracted or repelled by like or different charges, with some force, we can make that force do useful work for us. And that is electronics, is making things with some charge do something useful. Or just cool. So protons are stuck tightly in the nucleus of the atom. They're held in place by the strong nuclear force. Breaking a proton off of an atom is really difficult to do. Electrons, meanwhile, have a negative charge, but are just loosely floating around near the atom. They can be shared with other atoms, or just float around as free electrons. So typically what we're doing when we move around charges is we move around negative charges. Depending on what kind of material it is, it's either going to be really easy to move a charge through it, for an electron to travel from one atom to another through this thing, or really difficult. Things that it's really easy for we call conductors. The most common, most useful one is going to be any metal is going to be easy for charges to move through. Things like graphite and a pencil are also conductors, although not as well. They have a higher resistance, which is why you see them used in welding a lot, because when you try to move a current through them, they heat up a lot. And other things like plastic or air will be resistors. It'll be basically impossible to move any sort of current through them. They'll have very high resistance. The one we use most commonly in electronics is copper. It's got a lot of handy properties. It's easy to turn it into wires. It's fairly easy to melt it or plate it onto things. It's also not super expensive like gold would be. Whenever you have a charged particles moving through a conductor, that is called a current. So typically it's not the actual, but like the actual charged particles do move through it, but not as quickly as the current flows. Because typically you'll have a large concentration of negatives on one end, which will push away all the electrons that are close, that are distributed evenly through that, and even before any of these actual electrons move through the wire, the effect of them precedes them. And so we don't really think of the electrons themselves moving so much as just the charge that they're carrying. And like I said, we can do different things with that. Like light bulbs would be one obvious one. When you move a lot of current through something that's got a high resistance, it tends to heat up and glow. And I would gesture at these, but they're fluorescent lights, so it wouldn't really work. So this is actually a good slide for one of the more irritating things about this. So this is the basic, simplest electric circuit that does something, which is we have some source of voltage, which all voltage is a potential difference. One end of that battery is going to be highly negatively charged, the other end is going to be highly positively charged. So we have stripped off most of the electrons from one end and deposited them on the other end. So as soon as you connect those two things together with a conductor, it's going to want to equalize that. All the ones on the negative end are going to repel each other and try to move through the conductor to get to the positive end where they're being attracted. Because they really want to do that, they're going to be willing to shove themselves through the resistant electric lamp, which will glow since it's heating up. One of the more annoying things about this is, remember that what is actually moving are the electrons. So the actual electron flow is from negative to positive. The problem is, all of the symbols we use commonly for electronics assume that the current is going positive to negative. And when I say all, I mean about 85%. If you look at things like LEDs, or diodes in general, anode and cathode would, like the names of them would imply that the current is going reverse of the way it actually is. And so it's really easy to get turned around and forget which end is which. All I would really say is don't worry too much about it. Just conceptually think of it as some imaginary particle. I tend to think of it as like when you put water through a straw, you might see bubbles moving the other direction. You know that actually the water is moving, but the bubbles appear to be going the other way. Think of the positive charges as the bubbles where there are no electrons traveling the other direction. It's confusing. You're going to get turned around. It's because of a mistake that someone made about 300 years ago, and it's never going to be fixed. There's actually an XKCD comic about that. It's not an arbitrary decision that was made when people first started researching electricity in the 1700s about which charge should be considered negative, which one should be considered positive, and once they actually understood what was happening, it turns out that the electron should have the positive charge, but it doesn't. And since it's an entirely arbitrary human convention, so anyway, this is a circuit. If you were to disconnect this circuit, if you were to get rid of, say, this wire, then nothing would actually happen. The current wouldn't flow at all. Because in order for... Actually, here, I've got a good example of this. A battery. This battery is a voltage source. It'll source 1.5 volts. The problem is, even though this end is very negatively charged and this end is very positively charged, until I connect them with a conductor, which my hand isn't, nothing's going to happen. Because there's no way for the charges to transfer through the air. It will eventually... air does conduct a very, very, very tiny amount. It will eventually discharge itself, but practically it won't. So unless you have a complete circular path And I'll get back to a law that references that later. Let's say you had a complete circuit, it's not going to actually do anything. So there are two important sets of laws that govern how circuits work, what they do. The first one is Ohm's law. Ohm's law relates voltage, resistance, and current. And it is that voltage is the product of resistance times current. If you increase the resistance while leaving the voltage the same, the current drops, which makes sense. If you've got a set amount of force pushing charges through, and you're now trying to push them through a harder to push through thing, it's going to go through slower. Less of it's going to get through, right? A narrower wire has a higher resistance than a thicker wire. So if you take this battery and connect one end to the other with a wire, which you should never do, but if you did that, then the wire would heat up hotter if it were a thin wire than if it were a thick wire. This is why light bulb filaments are really thin. If they were really thick, then it wouldn't work. They'd have low resistance. They wouldn't heat up. The other two... So this is all one law. There are three formulations to this. That's one, is if you increase resistance while leaving voltage the same, current decreases. If you increase current while leaving resistance the same, voltage will increase. If you increase resistance while leaving current the same, voltage will increase. It's just a simple...
Ratio.
Huh?
Ratio.
Yeah, just like relation to those three things. So people get these three things confused a lot. Resistance relates to... How do we go backwards? There we go. Resistance relates to a path through the circuit. So one path through the circuit is going to have some total resistance across that path. Whenever you... So you can determine the... What am I trying to say? This circuit only has one path through it. And so we can figure out, if we know that the battery is, say, a 5-volt source, and the lamp has got, 10 ohms of resistance, we know the current is going to be 5 divided by 10, so 1/2 an amp. If you've ever heard the phrase, it's not voltage that kills you, it's amperage, that's kind of a weird thing to say. Without a high voltage, you don't get a high amperage. If you have a 1.5 volt source, it's not going to ever make as much current through a circuit as if you had a 50,000 volt source through the same circuit. The things are all interrelated. Voltage is inextricably tied to amperage through what it's actually trying to do. Everyone totally confused?
Nope.
Okay.
So amperage is just the unit we use to measure current?
Yes, I should mention that. So the three basic units for these: volts, voltage, the unit for it is volts. There's a unit for charge called the coulomb, and a volt is defined somehow in relation to the coulomb, and I forget how, because you basically never use coulombs ever. Basically, nobody cares about static charges in electronics. It's all about circuits and current flow. Static charges don't really exist, and static charges are what coulombs are measured in. Static is, by the way, a charge that is not moving. A current is charges that are moving through a circuit. Resistance, the unit is ohms. There's also a unit called mhos, M-H-Os, which is just ohm backwards, which is permittivity, I think, or conductance. You never use it. Basically, conductance is 1 over resistance. It's totally useless. And then the other is amperage, which is a measure of current flow. Which, again, none of these things are actually charged. They're all just things charges will do or things that will affect charges.
So all three of those different variables that you have is what gives you ohms?
No, R, the resistance variable, is measured in ohms. So let's go back to this circuit. So we've got three things you see here. Like this, you're going to measure in volts. So this could be a battery, like 1.5 volts. This is going to be some, you call it a load on that current. So that load would be measured in ohms. From those two things, from the voltage and the resistance, you can figure out what amount of current is going to go through. And I've got a demo that I'm going to do in a little bit where I can show you exactly how this affects it. If you put two light bulbs here instead, it would have the current, assuming that they're the same size light bulb. Because all these things are related together. They're all tied together with this ratio. This is probably the hardest conceptual thing to figure out in basic electronics. This and transistors. The other important law, or pair of laws, are really kind of common sense once you get this, and that is Kirchhoff's law, or Kirchhoff's laws. So Kirchhoff's laws, first of all, every node in the circuit, as much current goes into it as goes out of it. So a node in the circuit is just any point in there, like this corner, or this light bulb. Every amp of current that goes into this light bulb must go out of it. And no amps of current can go out of the light bulb that didn't originally go into it. Which makes sense, right? Think of it like the current is water, this is a closed loop of pipe, and this thing is a pump. That analogy actually kind of breaks down later on, but for something like this, it makes total sense. You can't, assuming the pipe has no leaks, the current's all going to go somewhere. The water that leaves the pump is all going to eventually come back in the pump. And there's not going to be any water entering from outside. Everywhere that you have current going into a spot, it's going to leave that spot. Which makes sense. And the other one is all of the voltages, all the voltage drops sum to the... all the voltage drops sum to be the same as the voltage rises. So if you consider that, let's say this spot right here, the negative end of the battery, let's just arbitrarily call that voltage level 0. Voltage level 0, you typically call it ground, but that's all ground means is we're just going to arbitrarily say that that node is 0. This, let's say it's 5. So this is a 5-volt source. So this point is 5 volts below this point. All that means is that here we go from 0 to 5. So we're 5 here, 5 here, 5 here. Here we go from 5 to 0 again, and then 0 all the way back around. We know that this lamp must have a 5-volt drop because there's a 5-volt rise on the battery. If there were 2 lamps, then each one would have a 2.5-volt drop. You would divide the voltage in half. If you put a voltage probe in the middle of the 2 lamps, it would show 2.5. Because all of the voltage drops, all the voltage changes must sum to 0. And those are Kirchhoff's 2 laws of circuits. Those two and Ohm's laws determine basically everything about circuits. And on that circuit, it's incredibly simple to figure out how they all mean, but on other circuits, if I have a marker, I can...
There's one right over here.
So this is the symbol for a battery. Don't worry about why it's like that. It's a symbol for a capacitor stacked on itself. We'll say this is 0 volts. And this is 5 volts, and then 2 lamps. So, right here, what's the voltage level? 5. Right here, what is it? 5. Because these two are connected by, we're going to pretend this wire is actually 0 resistance. Right here, what is it? Assuming the lamps are the same.
2.5.
Right. because each of these lamps is going to drop half of the voltage. And then right here,
Zero.
right. Where'd the- So suppose these lamps are different now. In fact, let's forget about lamps. Let's just say resistors. So this is a resistor symbol. And those lamps are resistors, they're resistive loads, but we'll just use this generic symbol instead. So this $200 and $300. So voltage right here,
No,
fine. What is it right here? Because now these two things aren't the same anymore.
right. 2.
It turns out that it's going to drop proportionally. The total resistance of this is 500 ohms. And the total drop is going to be 5 volts. If you were to pretend that each of these, like this is going to be 2 100s, this is going to be 3 100s, each of them would drop 1 volt because there's 5 of them in series, right? And so if you go for 2 of them, now you got 3, and then 3 more, now you're at 0. It turns out that you can just, you figure out based on whatever proportion this is to the total resistance is going to be what the voltage drop for that resistor is. Note that if this were 10, not 5, the voltage here would be 6, not 3. There's nothing magical about the fact that this is a 200 ohm resistor. It's just the relationship between this resistance to this point and the total voltage. Because again, Ohm's law. These things are all related. So this is actually a really handy circuit, like this particular one, because what this will do is translate if you've got a chip or something that needs 3.3 volts, and all you've got is a pack of 4 AA's or a USB plug or something that provides 5 volts, this is one way to get 3 volts out of it. It's kind of a crappy way, but it's one really easy way to do it. You just translate, you just use this, it's called a voltage divider. Typically you wouldn't do this for other reasons because you're the entire time wasting amperage just running this voltage divider, basically, in addition to whatever load this thing is. But that's one way to do it.
Can you walk through exactly how the current would flow through
Sure.
the circuit?
So, pretending that positive voltages are the ones that are going to flow.
Okay.
So, it starts out here, we have 5 volts, and we have a total load, let's pretend this thing is 0. You've got a total load of 500 ohms, so V equals IR, so equals V over R equals 5 over 500. So you've got 1/100th of an amp, or 10 milliamps. It's going to go through here. Part of it is going to, it's going to get slowed down some, trying to squeeze its way through this resistor. Okay? It's going to get slowed down some more, trying to squeeze its way through this resistor. And at this point, it has to be totally slowed down to 0 volts, right? At this point, it's lost all its potential. Because, so let me, here. Let me write this out a different way. This might make it a little easier to follow. So, it's a terrible drawing. So these are each 100. Okay. So this is our 200. This is our 300. Okay. So since these are all the same, it's just like the two light bulbs, right? You know that each one of them is going to drop the same amount. So this is going to drop it to 4 volts. This drops it to 3, 2, 1, 0. So 2 of these drop it to 3. 3 more drop away those 3. Because the total thing is 500, this is 2/5 of it, this is 3/5 of it. This drops 2/5 of the voltage, this drops 3/5 of the voltage. Whatever the original V was, this is going to drop 40% of it, this is going to drop 60% of it. So you can think of these as just being small rooms in series.
There is a formula for that.
Huh?
There is a formula for that.
Yeah, yeah. Go back to your Ohm's law and show them like so you have your 5 voltage, and then you would find your current, which would be the same throughout your entire circuit, right?
Yeah.
And then that would give you your
That's-
voltage at any point.
That's the other way to do it, is that because you know this is going to be 0.01 amps, you can figure out that this is going to be, you can figure out what this would, basically, so you know that the whole current is 0.01 amps, right? So you know voltage here is 5, you know current here, 0.01, you know resistance here is 200, so what is voltage here? You just plug the same thing in again and you get, yes?
You're saying this is a bad way to do a circuit, because you waste lots of power.
I'm sorry, what?
You're saying this is a bad way to do a circuit because you waste lots of power. But if your something there has a low resistance compared to the resistors, like not very much of it would go through the 300 actually, so you wouldn't be wasting that much energy. Can you just kind of game the system and put that 2,000 and 3,000 there?
The problem is that whenever you increase this to lower the amount that you're dropping off,
Yeah.
you have to increase this also, which is going to decrease the total current that gets to your thing you're trying to power. And so if you have a chip or something that needs at least 50 milliamps to run, then you need to have small enough resistors here that you're going to be wasting a large amount of current. It ends up that there's a thing called a linear regulator. It's a very common part number. It's like LM305, something like that. It's about this big. It's got a little metal tab on the back. That is how you would most of the time do it for powering something. This, though, would work perfectly for a signal line, where you're not going to be sending a lot of current down it. You're just going to be either bringing it to 3 volts or to 0 volts. For powering, you probably want to use a linear regulator, though. And again, that's what I've been told from doing this for a few years. That guy probably knows it for real.
When you say linear, you talking about like a voltage regulator?
Yeah.
Okay, yeah.
How does the voltage regulator work?
Good question. Ask
Is it
him.
resistance or
I
is
have
it a variable resistance or is it something else?
It's a
Yeah,
magic
it's
box
just like
as
a
far as I'm concerned.
resistor. It's like a resistor on itself,
Okay.
and it only lets a certain amount of
Okay.
Has feedback. There is a feedback
yeah.
compensates your loss at the end versus what you need, so it pumps more current to keep that voltage.
It's just a more efficient way of basically getting you
Yeah.
to drop, because there's more circuitry in it to kind of regulate.
On the other hand, it's a bigger, more expensive part. So
Yeah.
whenever you can use a voltage divider for something that's not using a lot of current, then it's probably better. The other way to do like drop to 3 volts, there's a part called a Zener diode. And I don't want to get a whole lot into that yet, but a diode is a thing that will only send current one direction and block it the other direction. Most diodes have a breakdown voltage where over a certain amount of backwards voltage, they will let it through anyway and then catch on fire. Zeners are special in that they will let it through anyway but not catch on fire. And so if you have a Zener diode that's got a breakdown of like 3 volts, then you connect that backwards to ground with your 5 volt thing. Anything over 3 volts is going to go out through the Zener, the rest is going to go forward to your part.
So it'll only let 3 volts through, that's it.
And you said this strategy is called a voltage divider?
Yes, this is a voltage divider.
How do you spell Zener?
Zener.
Quick question, you might have mentioned this when you were showing the slide. So you were showing the Ohm's law, and it's basically the variables I, R, and V. V is voltage,
Mhm.
R is resistance. I didn't get what the
I
I
is
was.
current. For why it's I have no idea. It just always is. So up until now, sorry, this isn't erasing very well. Up until now, we've only talked about components being in parallel, or I'm sorry, in series. So we have, well, for the most part. So we have all these different things, all these different resistors that are one after the other in series. By the way, as far as naming goes, volts are called that because the first person, they're named after somebody Volta.
Alexander Volta.
Alexander Volta. Ohms are named after somebody Ohm.
George Ohm.
Coulomb
Cool.
and amps are ampere. That one I...
Yeah.
George?
I think it's the last name of the person that made it.
Huh?
It's the last name of the person that made it.
Yeah.
They're all
They're all named after people. Okay, so 5 volts. Okay, my question for you guys. Is this going to have more or less current going through it than the one that had both of them in series?
Same amount total.
No, actually.
more.
More. Because think about water. Now it's got 2 paths to go down. When it was going in series, it had to squeeze through one narrow pipe, then another one. Now it can split itself and go through 2 narrow pipes. And the formula for this is that the equivalent resistance of this mess is the sum of the reciprocals. So you can figure out from that that these two would be 250, which is so this would be the same as having one 50 ohm resistor. And so you can figure out from those 2 laws, if you have, oh, by the way, because this is R equals 50, we can figure out the current, and then with the current, figure out what the voltage is going to be at each node in the circuit, and so on. If you take a college physics course, you're going to do this until you're sick. If you take a computer engineering course, you're going to do this until well after the point that you're sick. But from these 2 laws, if they're in series, you sum the resistances. If they're in parallel, you sum the reciprocals and take the reciprocal. From that, you can figure out the equivalent resistance of any network of resistors. Or you can train a computer to do it for you and never do it again.
Ross, real quick, could you maybe explain to them again, like the equivalent circuit is what you were saying? Maybe draw that real quick, and
Yeah,
so it kind of makes sense.
So this is the same as if we had done as if we had done 150 ohm resistor. These 2 circuits are going to have the exact same current in them. The only difference is you can put, a component here and add on to it. So, trying to think. That's about all I had, other than just questions.
Kirchhoff. You mentioned Kirchhoff earlier.
Yeah.
How in one when the current going in one node equals the sum of them coming out.
Yeah. Current is conserved basically. You can't create or destroy current. There's gonna be a constant amount of current going around this whole thing. So all the current that enters this node from this line is going to go out here and here. And the same thing here. All the current that comes in from here and in from here is going to go out here.
But it's always gonna go back to 0 when it gets back to the battery.
Yeah, the voltage drops are always going to equal 5 volts for this because the total voltage that the battery gives you is 5 volts. So both of these together, 5 volts here, 0 here, 5 here, 0 here.
So, what are, why would you put things in parallel versus in series or vice versa?
Good question. So for that, by the way, these things are awesome. This is a snap circuits kit. So this whole kit cost, when I got it, about $50. Somebody earlier was saying they found one in a thrift store for $1. If you're curious about this stuff at all and just want to play around with it until you understand it, these things are great. I cannot recommend them highly enough. So the reason you put them in parallel instead of in series is, so right now I've got 2 light bulbs going like that, see?
Remember that the voltage on the node is always the same, okay? So over there it's always 5 volts on the top line.
Yeah.
As long as you put 10 of those, it's going to be 5 volts always. So you
So-
can power anything that is 5 volts.
So why would you wanna break it up and go to smaller voltage?
Now what do you notice? Well, that and they're both overall dimmer. Because, okay, so this is 200 ohm loads, 100 ohm loads in parallel. Because of that, we know that the overall resistance is going to be 50 ohms. So 5 volts, 50 ohms. So 5, 50, 0.1 amps, right? Each of these guys is going to get 0.1 amps. If we have them in series, now things are a bit different. Remember that the light bulbs are physical devices, they're not going to change. Pretend that I drew this over here. So now we have a total of 200 ohms in the whole circuit, which means I equals 5 over 200, which is 5 over 100 is 0.05, 0.025. See? It's a quarter as much amperage. Because the current going through the light bulb is what makes it light up, having a quarter as much means that it's going to be a quarter as bright. Furthermore, a lot of that voltage is going to be eaten up by this first one. Remember that both of these guys are dropping from 5 to 0 volts. So they're both getting an equal amount of current. Well, everyone's getting an equal amount of current, but this guy is dropping from 5 to 2.5, this guy's dropping from 2.5 to 0. It turns out that if you look at this, one is now brighter than the other one. See? And you can see the same thing. It's actually worse with LEDs. It's actually makes more sense with LEDs. But that's why you do things in parallel instead of in series, is to increase the amount of current going to each thing.
Why would you choose one over the other when it makes sense to do the parallel thing?
Maybe you don't want as much current going to one thing. Maybe you want to put a resistor in series with something to limit the amount of current that goes through it. So one common thing that people want to do as their first electronics project is make an LED glow, right? So here's an LED. I'm going to make this thing glow. Now, LEDs are special. LEDs are what are called non-ohmic devices. Up until now, the resistors we've been looking at are always going to drop an amount of voltage based on the current going through them, right? Because they follow Ohm's law. Not everything follows Ohm's law. LEDs don't. LEDs, most of them, this one, your standard just jelly bean part LED, will drop 0.7 volts, always. Which means that if you have an LED in this circuit instead of a light bulb, then what you have, this is the symbol for an LED, by the way. 5 volts here, 4.3 here, and 0. It can't be both 4.3 and 0. So what actually happens is that the current rises close to infinite. It shorts out, basically. It's what would happen if you just connected a wire across the poles of the battery, which will, among other things, fry the LED. So you don't want that. So instead, what you do, 100K is no good. 1K? No, 1K will work. So instead, what you do, you put a resistor in series with it. Now, it's going to be 4.3 volts dropped by this resistor, which we know is going to be some sane amount of current. So the LED will light up. You can barely see it because it's 100 ohm. It's the 1 here. Oh, hey, that's it.
So wait, if you had not put the yellow thing on there, would you?
I've fried the LED, yeah.
How are you supposed to know that?
By going through talk like
By
this,
frying a lot
or
of
reading a
LED.
textbook. Here we go.
I've heard a few LEDs.
800 ohm LED makes it better. The other one was 1,000.
Does it matter if the resistor is before or after?
It does not.
Okay. That's
It will, I mean, kind of, no, it shouldn't matter at all, actually.
It's the same.
Yeah.
It's all a circuit.
Because either way, you're still going to have 4.3 volts going through the resistor. Because the LED will always drop 0.7.
How do you do it?
Huh?
How do you do it? When you're building stuff, do you put that resistor on the other side or on the first? Or?
At this point, what I'm usually doing is laying out boards. And the best answer I can give you is how it best fits on the board.
All right. So you said that all LEDs dropped at 0.75. Can you run a bunch of LEDs in parallel?
Yes.
Can you make it so you don't have to put that yellow surfboard thing in? Or will you just have to always have one of those
You
in?
actually can if you have a 0.7 volt power supply. This is 2 AA batteries, this is 3 volts. But if you actually get a benchtop power supply, dial it to voltage source at exactly 0.7 volts and hook it up, it will glow and not fry. I've done it.
It's slightly wrong, it will go.
Yeah, basically. If you twitch the knob wrong.
But you can run those in parallel like that,
Sure.
just like you did with the regular bulbs, right?
Now what you can't do, and this is kind of interesting, what you can't do is share one resistor to 2 parallel LEDs. Good question. Because, go back to think in terms of electrons. Okay, so up until now we've been going clockwise for the last half an hour or so, right? Because that's how most of the time you think about circuits, is going from plus to minus. Think in terms of minus to plus. Think in terms of what the electrons are going to be doing. So let's draw this out here. I've got this circuit with 1 resistor and 2 happy little LEDs. The electron goes here, make its way through the resistor. Okay. Now it's got to take a path from here back to the positive pole of the battery. The LEDs are never going to be exactly the same. They're physical devices, they're manufactured for 10 cents a piece, they're not going to be exactly the same. One of them is going to drop 0.702 volts, one of them is going to drop 0.609. And so one of them is going to be slightly more attractive to this electron than the other one. And so all the current's going to go through that one. Because of the limiting resistor, it's not going to be enough to fry it, but this one's not going to light up at all. or the other way around. Nobody tell.
Is that why
So-
Christmas lights are crap?
Because the electron's gonna take the path.
Right. Electrons always take the path, well, electrons will take the path that is least resistance in proportion to the total resistance. Because remember, if they always took the path of least resistance, then the voltage divider wouldn't work. Some of them have got to go back down that 300 ohm resistor.
But here it's almost like a short.
Yeah, because these things are not ohmic devices. Basically, diodes and LEDs and semiconductors in general don't play nicely with Ohm's law. They don't behave the way that Ohm would make you think they do.
Are they okay in series though?
In series they are, except that, remember, they're going to light up based on what the voltage coming into them is. And so you're going to have one bright one, then a slightly dimmer one, then a slightly dimmer one, and so on. So the best way to do it is in parallel with one resistor per LED.
How does it know? I thought the voltage levels were arbitrary. How does the LED know that its voltage is higher than the next one's?
So you start with 5, then you get 4.3, then the
It's
next
not
one gets
really five,
4.3.
Like it might be 105. And the 100 you defined as the
But if it was 105, then you would need a really big limiting resistor. So
Well, the voltage is dropped from the previous LED in front of it, right? So
Yeah.
like if it was 105, you would lose the 0.7, and then the next one would only see 104.3.
yeah,
But I thought these numbers were relative. I didn't think that they were
Ex-
absolute.
so like I said, semiconductors are weird. LEDs will always drop 0.7 volts.
Yeah.
LEDs will also explode if they have more than a certain amount of current going through them. So let's say that it's 0.7 volts and half an amp, right? If you put 105 volts on the front end of an LED and then a normal resistor on the end of it, then it's going to go to 104.3, and that normal resistor is going to let through 17 amps and fry the LED. It's still only dropping that same amount, but so what you need is 5 volts but with a lot of current behind it.
So if you switched out those two LEDs right there for two bulbs, they would both light equally,
Exactly.
because they're not LEDs and not sapping the,
Right.
they're just running a current, not draining the current.
And you can do that because this thing actually came with 2 bulbs. I can actually show you that. So if I take these two, see, that's why I brought this thing. It's handy.
Can you assemble it in the air so we can all see what you're doing?
Yes, give me 1 second, I'll do that. I just gotta assemble it and then I'll show off the finished product. So I'm going to swap out this resistor for just a wire because the bulbs want more current to work. There. See, with 2 bulbs in parallel, they both light up. With 2 LEDs in parallel, they won't, because the LEDs, they're either going to work or not, basically.
But you wouldn't start a fire.
If you had, so here, I'll show you. Right.
I totally started a fire, so I'm like, how did I do that?
So as long as there is some resistor on there, that's a strong enough resistor, as long as you're limiting the current in some way, you will not start a fire. And really you won't start a fire anyway. What it'll actually do, if you actually try it, is it will flash really brightly for like a third of a second and then never work ever again.
It made a lot of really bad smoke, very toxic.
So, it is the kind of annoying part of this, is having to try and find all the little bits of wire with a snap.
Important side note over there is that the current always tries to find the weakest possible path.
Yeah.
You can explain that on the circuit, right? And that's when you do a short.
Which
Okay,
brings
so see
us
how
to
one
the first
is much
rule
dimmer
of
than the
building
other?
electronics.
Yes, the red is brighter.
Always
Yeah.
buy more than one.
You're saving
Actually,
shipping.
it shouldn't line up at all.
Which one? the
Yes.
Yeah, the green one should just be like barely working, but it's actually. Huh.
Shorted.
Yeah. No, for the beginners in the room, you'll find that your part cost is cents. What you're paying for is shipping.
Yeah.
So never buy, like, my rule is I don't buy less than $5 of something. And if that means I end up with 50 of them, I now have 50 of them.
Is one of your laws breaking?
Yeah, it shouldn't.
They're more like guidelines, really.
Well, they do both light up.
Yeah.
That's strange.
Shorted.
What, now can you change out like, let's say the green board for a bulb? I mean, because that thing, the LED just decreases the amount of circuit current.
Well, what I want to try is if I put the resistor on the other side, and I bet now it won't work. I bet now it'll do like I was saying it should.
Because it's running positive versus negative.
Huh. I mean, I did this before. It didn't actually work. But you can see it is still lighting up with LEDs.
Sometimes like.
Shorted.
So yeah, I mean, from the perspective of this chart, one of these should light up, one of them shouldn't.
I thought you said one would just be dimmer, because it would get less power, or less current.
For light bulbs, yes.
Oh.
Well, no, for parallel it should be the same because it's the same amount of current.
Maybe they're using the wrong resistor.
I don't know. That is strange. It's 100. I don't know. That is strange. And often that will happen. Often you will build something and it won't work for some non-obvious reason, or it will work for some non-obvious reason. But this whole stuff's complicated.
So you can exchange one of those for a bulb, and everything should still work, right?
Yes, except the bulb probably not going to light up very much because we have the resistor in series with it. So the bulb needs a lot of current to operate. So if you have a resistor in series with the bulb, it's probably not going to work.
What would happen if you have a flat a light bulb and then LED? Would the light bulb not get as much power, or like not power at all?
Well, I'm actually building that right now. I'll show you. So what happens is that the LEDs will probably light up. Oh, or not. So here, I have actually built that here. What's happening is because the resistor is in here, it's keeping there from being enough current flowing through here to light the light bulb. If you replace the resistor with just a wire, then it'll light the light bulb. See, it just bypassed the resistor. The problem is if we do that, that's going to be too much current for the LED, and so it'll explode. By the way, when I bought this, it actually came with a note in the box saying, you know, have fun with your new kit. Whatever you do, don't connect an LED directly to a battery because it'll explode. I thought it was kind of funny.
I'm sure it's happened a few times. Until I got sick of replacing parts.
This is kind of the part where my level of expertise with this breaks down because I don't know that much about how semiconductors work. I can tell you a little bit of what I do know about them, but you're going to be better off consulting somebody who's an actual engineer or a book. So basically there are two types of semiconductors. There's the N type and the P type. And what these are is so everything up until now has been either a conductor, like a wire, or a resistor, like a piece of plastic. A semiconductor is a conductor if it is touching a thing that is positively charged, or for the other kind, negatively charged. And so the idea is if you take an N-type and a P-type and stick them next to each other, then they'll conduct charge in one way but not the other. Because you'll have, the charge going in, the current going in, allowing this one to be a conductor, and so it goes through. Current goes in the other way, you don't have the current allowing this side to be the conductor because this side's resisting it, and so it won't go through. And so that's what a diode is. That's why the symbol for it is this little kind of arrow thing, is because it will allow it through one way but not the other. And an LED is a light-emitting diode. But that's why they're not. That's why they don't obey Ohm's law. Is because they're semiconductors and are weird and made of magic. The other thing you do with semiconductors is if you have 3 of them, an in and then a p and then another in, or vice versa, a p and then an n and then another p, you can make what's called a transistor. So I just want to touch on this a little bit. NPN and PNP transistors. These will let current go through if this side is negatively charged for the NPN, unless I got that backwards.
That's right.
Okay. The other one will let current go through if this side is positively charged. And so what these are switches that you can control with another current. They're electrically controlled switches that are just one solid piece of stuff. And by connecting switches together in really complex ways, you can build computers. That's really all a computer is. It's just an agglomeration of billions of switches. So these things, you often find them in stuff that does any sort of intelligent, making something blink, or switching something on and off, anything like that. Chips are going to be hundreds of thousands of these. You can also use them to amplify weak signals. Like, you ever heard of a transistor radio? All that is